everyone. Thank you for the warm welcome. Saw some very interesting talks over the last, I guess I arrived yesterday and today, so thank you all. So I'm from Canadian Nuclear Laboratories. Most of you have probably never heard of it. It's a Canadian Nuclear National Lab. We are a combination, we're a private entity now owned by the government. We primarily do nuclear research, but also other energy industry related research for both the government and for private industry, operating under a commercial model. So picture of us, the lab, it's about 3,000 people, a couple of reactors there in the beautiful Canadian wilderness. So I'm going to be talking to you about nuclear fuel modeling. So what is it? There's a pictorial diagram here. This is of a Canadian nuclear fuel design, but it's really very similar for most of the rest of the world. Essentially, there is some solid ceramic fuel pellets inside a metal tube, hermetically sealed, placed inside a nuclear reactor, cooled by high pressure water to some degree. For the layman, the ceramic gets hot, transfers heat to the metal, transfers heat to the coolant, that's used to boil water, hot water is used to produce power. So what happens to the fuel? Well, as I mentioned, when it's placed in the reactor, it undergoes a nuclear reaction, fission, that produces heat in the fuel. The fuel is the pellet. That produces a high temperature and high temperature gradients. These ceramic pellets actually have very poor thermal conductivity, which means we need high temperature gradients to drive the heat out. High thermal gradients and high temperatures means a lot of thermal expansion. There's also some nuclear specific phenomena. When fission occurs, it splits a uranium atom into two separate atoms. We call those fission products, and those accumulate in the fuel. So as we've manufactured this beautiful, pristine fuel, put it in the reactor, and with time, it fills up with all these other elements that we have to accommodate. It leads to a lot of very interesting effects. There's all kinds of cracking inside the ceramics. Ceramics are not particularly durable or tough. We have contact between the ceramic and the metal cladding. We have radiation damage. There's high energy fission products. There is gamma radiation and neutron radiation, and this changes the microstructure of all the materials. We have swelling. If one atom is split into two, it needs to be accommodated inside the crystals. Two atoms take up more space than one, and that causes macroscopic swelling. Some of the fission products are even gas, and I'm going to spend a fair amount of time talking about this later on. Some of them are xenon and krypton. These don't like to react chemically, they like to occupy a lot of space, and they form bubbles or pores inside our fuel. We have corrosion issues, so we have very high temperature water in a radiation environment. That leads to radiolysis products. That leads to corrosion on the outside of our metal. Hydrogen also diffuses into the metal, which changes material properties. And as I mentioned, if we accumulate fission products, some of those fission products are radioactive, which means in addition to the evolution of our elemental composition due to fission products, we also have radioactive decay that needs to be accounted for. So this is a very complicated system. This is a picture from the 80s. So in the 80s, this is the type of multiphysics coupling that we were doing in the nuclear industry. Everything depends on everything else. So, if we take a quick look, the number of arrows into the fuel temperatures box is quite extreme. So, for my PhD thesis, I took on modeling this sort of system with COMSOL Multiphysics, and actually had a fair amount of success, and I'll show you some results of that later today. But first, why do we care? Well, nuclear fuel is one of the limiting factors in the performance of nuclear power plants. It limits how much power we can get out of any given reactor, and that costs dollars. If we can increase the power rating for the reactor, that's worth millions of dollars a day. Many reactors. Also, if we can increase the reliability of the fuel, we can allow reactors to go up and down in power, which allows us to accommodate more green energy on the grid. It's called load following. Nuclear fuel is one of the limiting factors as to how quickly you can go up and down in order to accommodate that thermal expansion, the cracking, without damaging the fuel. And so at the end of the day, it costs money and it affects the environment. If we can have more nuclear power and we can accommodate more green energy, and prevent many, many tons of greenhouse gases from being emitted. It also has consequences for nuclear accidents. The fuel's the primary barrier to the release of radionuclides. So, if we can design better fuel, we can prevent Fukushimas from happening. And the last point here I'd really like to stress is that nuclear fuel is designed to be replaced. It's consumable, right? When you fill up your car, you're adding gas to it. Same thing with nuclear reactors. We take the nuclear fuel out, put fresh fuel in. So this is an actionable plan. This is a way we can actually feasibly make nuclear reactors better. They're expecting new fuel. Maybe we give them an upgrade when we put new fuel in. So, for my PhD thesis, I developed a COMSOL model that we've called FAST. That stands for Fuel and Sheath Modeling Tool. The sheath is the fancy word we use for the cladding, the metal that provides the support and hermetic seal. There's quite a bit of physics involved in the model. So we have 2D heat transport, both in the pellet and in the cladding. We have linear elastic materials, but then we also have to add on top of that thermal expansion, densification, fission product swelling, creep, relocation, which is a type of cracking phenomena. We have the fission gas, which causes additional swelling. We have a gap between the solid pellet and the solid cladding filled with gas. So we have to transport heat across that. That involves calculating gas composition, gas pressures, gas temperatures. And the cladding. In nuclear reactors, we primarily use zirconium-based alloys. Those are very interesting because they're HCP, so they're hexagonal close-packed crystal structures. What that means is they're anisotropic. So the crystal, if you pull on it in one direction, behaves very differently than if you pull on it in another. And we have to account for that in our models. So here are some sample results. What you're looking at here is this shape here is a pellet with another pellet right next to it, and they form a long stack. On the outside, we have the cladding, and then we have an end cap on the end. The color scale in the top figure is the temperature. So this actually isn't operating at a very high power. Its centerline temperature is only about 1600 Kelvin. During high power operation, we can reach in excess of 2000 Kelvin. So there's a lot of really interesting physics that happen. As a result of the thermal expansion of the individual pellets, we get this interesting phenomenon called hourglassing. That's shown in the bottom figure. I've exaggerated the radial displacement to give you an idea, but it produces a wavy pattern in our cladding. So that's because the ends of the pellet bend outwards in order to try and make room for the hot material that's kind of at the center of the pellet. That causes increasing cladding strain that we have to model. So if I look at the radial displacement along that surface, so going back, if I plot the displacement along the outside of this line, I end up with something like this. We have the effect of the end cap. We have a low power pellet on the end. Then we have a pellet where some of the heat is moving in the axial direction. And each of these spikes corresponds to one of those areas where two pellets meet and push into the cladding. The overall linear part is due to the gradient in the power based on where it's in the reactor. And then at the end, we have an empty space to accommodate the fission gas. So that's called the plenum. Some other results from the model, we can see some very interesting stress and strain fields. So the first at the top is the hydrostatic pressure in the pellets. We can see that it's very high in the center because it's very high temperature in that region. It wants to expand thermally, and it's being constrained by the rest of the pellet, which is much colder because it's closer to the coolant. So we see this pattern repeating in each of the pellets. That leads to an interesting distribution of the von Mises stress. On the outside of the pellet, it's being pulled apart, which causes a large tensile strain. And because it's lower temperature, it has higher Young's modulus, leading to higher stress on the outside. If we look at the axial creep is a highly temperature-dependent phenomena, and so that occurs primarily at the center in order to try and relieve that pressure. So we see very interesting, very rich spatial fields when we're trying to model these phenomena. I've also done some work with 3D models as opposed to the 2D. In this case, we were looking at what happens if I apply a very high temperature on one side of one of these tubes than on the other. So you could envision a situation where one side's in water, one side's in steam. You're going to get more thermal expansion on the side that's hotter. That's going to cause it to bend. So we were looking at that in the top figure. And in the bottom figure, same model, but instead of applying a thermal gradient across the coolant, we actually just applied mechanical loading. So this is a very complicated compound beam structure because you have discrete pellets inside the tube. The pellets can move around, but will eventually lock, increasing the stiffness. So for the second half of my talk, I'm going to discuss some more recent work I've done on grain boundary fission gas modeling. So I kind of alluded to this a little bit before, but some of the fission products are gas, roughly 30%. So that xenon and krypton doesn't want to stay inside the grain. It's very insoluble. So it diffuses around and eventually makes its way to the grain boundary. It doesn't really want to be high pressure at the grain boundary, so it starts attracting vacancies. And if we look at the figures here, this is from 3 different time fuel that was taken to 3 different times in a reactor. Initially, these grain boundary bubbles form very small, isolated bubbles. This is good. The small bubbles have high pressure. They really keep that gas small, and they don't allow a lot of swelling. With more time, they grow and they start interconnecting, and we see that in the second image. We have some very small isolated bubbles, but then we also have some much longer high aspect ratio bubbles. That's because nearby bubbles combined. And in the last picture, we have a very interconnected network. And what that means is all that gas can actually start escaping the fuel. You have long-range connectivity. So we decided to try and develop a model of this. The traditional approach has been to look at it on the scale of a pellet. So you're not actually looking at the microstructure, you're just solving macroscopic fields like burnup. This is the amount of gas on the grain boundary. This is the radius of the average bubble on the grain boundary. This is the number of bubbles on the grain boundary. And if you take these two properties and multiply them together, you get what fraction of the grains are covered. But there's some issues with this. It doesn't actually model the details we saw in the previous picture. Some of the grains are large, some of the bubbles are very large, and some of them are very small. So what if we could model the individual bubbles? And this is a problem that traditional phase field could be applied to, but it's very computationally intensive. So we developed a new type of phase field model intended to only model things confined to surfaces. Being a COMSOL user, my first instinct was to implement this in COMSOL. It follows the traditional phase field methodology of you write out what is the energy of my system, you let COMSOL take the derivatives, tells it what direction to go to lower the energy, and then you can end up producing some very pretty pictures and even videos, if I can make this play, like this. So what we're seeing here is initially we had a random distribution of the bubbles on the grain boundary surface. That means we have a lot of surface area. The surface area has surface energy associated with it. So that's a high energy state, and it wants to minimize its surface energy. So the first thing it does is it smooths itself out. It starts pulling itself together to form kind of smoother bubbles. Then it starts decreasing the aspect ratio of the bubbles. Finally, they start collecting on the edges and the vertices. And this is actually a phenomenon you've probably witnessed before. If you've ever, after the rain, played with bubbles on the hood of a car, it's exactly the same physics, just slightly different timescales and temperatures. In this case, we're looking at a single grain of uranium dioxide, not water on a car, exactly the same physics though. So how did we do this? Well, this image here kind of reflects the traditional sharp interface model. This is the Young-Laplace equation. Basically calculates things like, what is my meniscus angle? Then we said, okay, well, let's define the surface S, which is removed from our computational domain. So you can think of X as the interface between the grains, but it's also where our mesh exists. We then describe that surface S by how far away it is from that surface, and then allow COMSOL to solve for the unknown variable H. And I won't get into exactly how it works, but here we have this diagram which indicates how we calculate the surface area in COMSOL. If anybody's interested in the math, we have a paper published, but I won't go into it here. We could see some time evolution of two bubbles joining. So the bubble on the vertex here is larger, so it's at a lower chemical potential. The color scale here is chemical potential. Small bubbles have a lot of surface area relative to their volume. It means it's a high energy state. So they want to combine these two bubbles to form one larger one, therefore eliminating some of the surface area. And we see the time progression of that here. Once the bubbles connect, they begin to smooth, get rid of the high surface area region here. They pull together, and then they will eventually return to that equilibrium shape we kind of see in this image here. We also did some validation work on this new model. This is just looking at a single bubble on an infinite plane. Can we control the contact angle? And what we see here is that yes, we can. On the left side, we actually see a zoomed in region here, and we can control the edge of the bubble. How sharp is that edge? That's a controllable parameter in our model. And as my last slide, I'm going to talk about some other interesting, or at least allude to other interesting effects. So this image on the side here that looks like an eye, that's actually a cross-section of nuclear fuel after it's been irradiated at very high powers and very high temperatures. The pores have actually migrated towards the center, up the temperature gradient. What's happened is some of the uranium on the hot side of the pore has evaporated and deposited on the cold side of the pore. What that does is it forms these really long columnar grains we see in this image and kind of pictorially described in that image. We have the fission product precipitation. So there's literally dozens of elements produced inside nuclear fuel, and that forms complicated chemical phases. We have phenomena called high burn-up structure, which is where one grain breaks off into many small grains. Cladding corrosion, pellet metal bonding, oxygen transport, many interesting multiphysics phenomena that we can investigate with this software. So I think that uses up all my time, so I'll end here. But if anybody has any questions, feel free to ask them or meet up with me later, and I'm happy to discuss them with you.